Okay, here we are with part 4 of our Introduction to Mass Spectrometry, recorded for Analytical Biochemistry in 2021. So previously we've been talking about hybrid instruments that have been typically used to study biomolecules. So quadrupoles linked to time of flight, quadrupoles linked to Orbitraps, that kind of thing. Now, in the last couple of years, there's been an additional type of mass analyzer that has become increasingly available on commercial instruments that is complementary to separating ions by quadrupoles to be measured by time of flight instruments and Orbitraps. And these are ion mobility mass spectrometry. And so I'm going to give you a very brief introduction on the types of ion mobility instruments that are out there. But first, we're going to talk about what ion mobility actually is. So we talked about time of flight before, and so time of flight, all of the ions start at a certain point and then they drift through the flight tube and they separate based on their mass. Now, in this case of ion mobility, rather than separating out by their mass, they separate out mainly by their shape, or what can be called collisional cross section, which we'll come back to in a second. But essentially, all of the ions start at the same point outside the drift region of the ion mobility cell, and they move through the mobility cell, traveling along with an electric field. And there's often a gas inside the ion mobility cell, and the more compact the molecule is, the faster that it's able to migrate through the ion mobility cell, and you get separation out. So the graph part on the sorry, I'll just get my laser pointer. The graph part out here where you have the most compact one coming out first. And so this is measuring drift time, where zero time is here and later time is here. So the more compact ones come out first, the larger ones come out later, and the very largest ones come out later on. It's not really related to mass, it's more related to the shape of the molecule rather than its mass. Now, what you can do with this, it's really powerful. So what you can do, as seen in this example over here from this website, you've got the same molecule here in both cases. These would be isobaric molecules, so they would be exactly the same mass, and you would not be able to tell the difference of them between them in an Orbitrap or in a time of flight mass spectrometer. The difference is the arrangement of this bond. So in this molecule, this is in the cis position, and in this one, it's in the trans position. Ion mobility can separate these populations of different stereoisomers out from each other. This is a pretty extreme example. You've got to work pretty hard to get complete baseline separation of things like this, but this shows you what kind of power you can actually get up to in these instruments. So like I said, this has been commercialized in a number of different ways, and there's a number of different flavors of ion mobility that I'm going to go through as we go through the video. So the first one is these differential mobility separations, which are implemented as Selexion in SciEx instruments and as field asymmetric ion mobility spectrometry in thermo instruments and a few other instruments. These are atmospheric pressure devices. They work slightly differently to each other, but they both rely on this compensation voltage to let different ions move through the region and then into the mass spectrometer. The same in this case, where the ions come in and different compensation voltages allow different ions to travel around the separator and then into the inlet of the mass spectrometer. So these are atmospheric pressure devices. You bolt them onto the front of your existing mass spectrometer. There's two other types. One which is timed ion or trapped ion mobility, which is on Brooker instruments that we'll talk about later on. These are not bolt-on, they're actually physically on the inside of the instrument, although they are the first thing that the ions encounter before going through the quadrupoles and time of flight. The other variation is travelling wave, as implemented in Waters mass spectrometers, and Waters have probably got the longest history in ion mobility instruments, where the analytes come through the sprayer here, they then get focused by this ion guide, they can be selected by the quadrupole, and then they can be either fragmented in the trap or subjected to ion mobility in this cell, and then fragmented, and then those molecules are measured by the time of flight detector. So ion mobility can be considered in the middle between liquid chromatography and whatever ion detection method that you want to look at, with the amount of time that it takes to do these separations and measurements. So chromatography typically happens where all of the molecules of the same peptide elute anywhere from 5 to 15 to 30 seconds from the chromatography column. So you've got a lot of time to sample or measure the same molecule as they come out of chromatography. On the other end, the time of flight detector and Orbitraps, they're running at sub-milliseconds. They're running at microseconds and picoseconds to be able to do the detection. So you can have quite a number of mass scans done by a TOF or by an Orbitrap across an elution peak. IMS fits in the middle where an IMS run takes microseconds, so you can drift the ions and separate them and do multiple scans with the TOF or with the Orbitrap, so that you can have a collection of ions, but then they come out of the drift cell at different times, so that you can do sequential scans on what's coming out to build up a bigger picture of what is actually in this chromatographic peak. So first one I'm going to talk about is travelling wave ion mobility. This is mainly implemented in Waters instruments, and you can see from this diagram that I've borrowed from Waters that the electric field travels in a wave. And so the ions that all start together when the final ion goes out, and the animation starts up again, when they try to get the ion, sorry, I'll get the animation to start again. There we go. So all of them start together, and you can see as the wave carries them along, different ions of different shapes get separated out. They get carried forward by the wave a lot faster than other ones. And this happens on a millisecond time scale. So this is massively slowed down. But you can see how this works. Again, in this kind of cartoon that runs very fast, all of the ions come in at the same time, and there's a wave of electric field across the ion mobility unit that then causes these molecules to separate out from each other. And you can do a TOF scan on these individual ones that come out to be able to get a mass spectrum for each different drift separated ion. Now, because this is actually really reproducible, what you can measure is the collisional cross-section of these ions. And the best way to think about this is actually to take the shape of an ion and spin it in space. And that is what would be the collisional cross-section that then gets separated through. What can this really be useful for? Well, for structurally related molecules that have the same mass or are isobaric, especially lipids. It's very, very useful for that. So as an example of this is not a lipid, but it's actually a drug. In this side of the diagram, what we have is a low energy scan of the intact molecules, and then a high energy scan of the fragments. So when you have molecules in the same scan here, the fragments of both of these will end up in this mass spectrum because there's no separation between the two of them. If we do, if we actually then use ion mobility, and in this particular geometry, the ion mobility happens before the quadrupole selector and before the collision cell, we can isolate this drug from the other one. It's exactly the same chromatography. You can see that it's the same retention time, but all we're doing now is drifting the ions that are coming into the machine. So this particular compound has a different drift time to this one. So we get these, and we do the same thing when we fragment. The precursors are separated by drift, and so when this gets fragmented, the fragments have the same drift time as the precursor. So we can assign the fragments to a particular structure. Now, it's actually been extended on from the device that we saw, which is just a linear device where it's about anywhere up to 90 centimeters long. Typically, they're about 25, 30 centimeters long. And you have them in the instrument and you just drift the molecules through there. But what Waters found is that you can actually create these cyclic IMS devices where the ions come in and they get diverted by this array where the ions come in here. They could go straight through, but what you can do is you can divert their flight into this cyclic IMS device, and you can get them to go around and around and around as many times that you want. And the more times that you go around, the more you separate these molecules. So these molecules are actually isobaric molecules. They have the same mass. They are coming into the cyclic IMS at the same time, and after 5 rounds around the cycle, 5 times around, you get them separating out into these 3 peaks. If you keep going and you get out to 18 passes, you can see that you now have isomers, different structural forms of even these things that are separating out as you get more passes. What you can eventually do is actually get them then to come back and go out the other side through these transfer optics and into the detector to measure them. You can also do fragmentation on the way out and other really neat experiments. So this is very, very powerful stuff. The next one that I want to talk about is this idea of field asymmetric ion mobility spectrometry, better known as FAMES. And this has been pushed for a number of years by SciEx and more recently by Thermo, again as a way of fractionating the ions that are coming into the mass spectrometer to be able to get cleaner data from the sample and potentially more data from the sample. So what happens in this is you've got these electrode plates on either side, or in this case, you've got this central electrode with an electrode plate around the outside. Here's the electrode plates here. And what you can do is you can alternate a waveform across these 2 plates. And as you alternate the waveform, different molecules will move toward the plate at different rates, depending on this compensation voltage. So in this particular case, at a 0 compensation voltage, the blue ion will travel through, whereas the others have unstable trajectories and they won't exit the cell. What you can do is you can vary the compensation voltage so that you can get this ion to come out before this ion, and do that kind of separation. And therefore have a cleaner ion signal to then do fragmentation or measurement on. So this has become very, very popular on these instruments to try and fractionate peptides, especially in complex proteome mixtures. The last one that I'm going to talk about is this idea of trapped ion mobility, and this has become extremely popular over the last couple of years with Bruker releasing an instrument called the timsTOF, and it has become almost the benchmark instrument if you want to do proteomics. And one of the reasons for this is this idea of being able to trap and accumulate all of the molecules of something before you pulse it into the instrument. So you have this TIMS device, which is at the front of the mass spectrometer. Here's the ion source. All of the ions come in at the same time, and you can use different voltages and radio frequency to separate these ions out from each other, but also to accumulate them within this device before you scan them out into the rest of the machine. So it's a similar idea to FAMES, where you can let one thing through and get a mass spectrum, or you can start to stagger the exit of these molecules. So in this particular case, we set it so that we accumulate the red ion and we pulse that out and we measure it. The yellow ion, we pulse that out and we measure it. The green, the blue, and we can measure them all sequentially. And so what we can do is we get a far cleaner spectrum than if all of these were going through at the same time, especially in data-independent acquisition, which we're going to talk about in the last lecture of this series. So that's all I'm going to say about ion mobility. There's numerous videos out there on the web that explain this in far greater detail and can show you the power of this device. But it is becoming a lot more prevalent in newer and newer instruments, and a lot of people who are buying instruments for biomolecule detection, especially shotgun proteomics, are buying them with ion mobility in there to increase the depth of analysis that they can do on a very complex sample, and also to speed up the analyses, because rather than relying on the chromatography to separate out molecules, you can speed up your chromatography, have more molecules coming into the machine at a particular moment in time, and have them separated by the ion mobility, which is a much faster separation mechanism than chromatography. So just to summarize, ion mobility is another separation method. It is somewhat independent of mass, not completely, but somewhat. It is most often used as another dimension of separation to increase the depth of characterization, as I just described. And it's also of extremely high use with molecules or mixtures where there's a lot of isobaric molecules, especially lipids, where the molecular size, the molecular weight is the same, but the structures are different. Different double bonds at different places, which cause the molecule to have a different shape and therefore a different collisional cross-section, and you can use that to separate those molecules out and get more depth of understanding of what's going on in your particular sample. So far we've done 4 parts, and we're pretty much at the end of how these instruments work, and we're going to move on to the practicalities of how to use these instruments. So what we've talked about so far is that a mass spectrometer can be used to measure the molecular mass of a charged ion in the gas phase. And because you can fragment these ions, you can work out the structure, or you can differentiate isobaric compounds through fragmenting them and measuring their fragments. Now, the vast majority of the time, we're going to use electrospray coupled to chromatography to get those biomolecules into the mass spectrometer, because we can use chromatography to reduce complexity or to concentrate the molecules into a very small volume and a very small elution time to maximize the sensitivity of the mass spectrometer. The other method that we can use to get biomolecules into the mass spec is using MALDI, but nowadays that's more used for things like biotyping and for MALDI imaging. And I guess the most important thing that I want you guys to remember is that this is all to do with manipulating charged particles in electric and magnetic fields, and you can use that to do all sorts of wonderful things with ions to analyze them. And so we're going to continue on in part 5, where we're going to start talking about the applications of mass spectrometry for the analysis of biomolecules. So I will see you then.